Okay, so I think let me see here. Okay, I think I'm in business now. Okay, so let me go back to the PowerPoint. All right, so as I was saying, basically the combined gas law, hold on, what's this thing? I hate when this happens. Okay, so the combined gas law combines all these equations here, taking into account that all the possible variables are changing: the pressure, the volume, the number of moles, and the temperature. So this here is basically the resulting equation, right? So that's the ideal gas law, not the combined gas law, I misspoke. And so we have the equation here, which takes all these variables into account. PV divided by NT is equal to a constant, and that constant is given a special name, which is the molar gas constant, and a special symbol, which is R, all right? And in most textbooks, you'll see it expressed in this way. It's the same thing. PV is equal to nRT. R is a constant, as I said before, and the value of R is dependent on actually the units associated with the pressure, volume, and temperature, and the number of moles. So if the pressure is in liters, if the pressure is in atmospheres, and the volume is in liters, and of course, N would be moles, and the temperature is in Kelvin, then the value of R is what you have right here. R is equal to 0.08206 liters atmospheres per mole Kelvin. Now, for our purposes, we're just going to use the value of R rounded to 366. So the value of R that we'll be using would be 0.0821, but this is a combination of units that you need to keep in mind, all right? Liters atmospheres per mole Kelvin. Now, there are other possible values of R depending on other units that are used. So for example, if the pressure is in atmosphere and all the other units are the same, volume is in liters and so on, then as we said before, R is equal to this. But if the pressure is in torr and all the other units are the same, then R has this value right here. And then a special case, which we're going to see later on, is that if pressure is in pascals and volume is in meters cubed, then R works out to be equal to 8.31 joules per mole Kelvin. All right, so these are all possible values of R depending on the units of pressure and volume that are being used in the ideal gas equation. In the vast majority of cases, for all purposes, we'll be using this value of R right here, all right? But there's one particular case later on in this chapter where this is the value of R that we have to use. And I'm going to explain why that is important when we get to that particular topic. Okay, so let's look at some examples right here. So the question says, and this is basically based on the ideal gas equation. So the question is saying here, what is the pressure exerted by 0.508 moles of oxygen in a 15.0 liter container at 303 Kelvin? So in this particular case, the equation that we're going to use is, let me choose the correct color. Okay, so the equation that we're going to use, of course, is the ideal gas equation, which is PV is equal to nRT. What the question is asking for is P. So if we rearrange this equation, we're going to get P is equal to nRT divided by V. And then we have to put the numbers in. So P would be equal to the moles, which is 0.508 moles, times R, which is 0.0821 liters atmospheres over mole Kelvin, times the temperature, which according to the question is 303 Kelvin, all divided by the volume, which according to the question is 15.0 liters. So, and this explains and underscores the reason why I'm a stickler for units, right? Make sure that you include your units as a part of the setup, because here you're going to see how the units cancel out each other until you get one final unit, which would be the correct unit for the answer for the question. So the moles will cancel out here and here, the Kelvin will cancel out here, and the liters will cancel out here and here. So the final units would be in atmosphere. So let me do the calculation here. So it's going to be 0.508 times 0.0821 times 303 divided by 15. And according to my calculation, this works out to be equal to 0. Okay, so we need to round out to 3 sig figs. So this will be 0.842. So 0.842 atmospheres. All right. And that's basically how that is done. Okay, any questions about this? Any questions? Any questions?
No questions.
Okay, so the next example is, in this case, a bit different. For one, it's asking for the volume for a particular gas. It gives you the mass of the gas. It gives you the formula for the gas. It gives you the pressure, and it gives you the temperature. But in this case, they gave you the pressure in torr and the temperature in Celsius. So there's some conversions that we have to perform in order to do this question. So again, the equation is PV is equal to nRT, but this time the question is asking for P, which is equal to V, which is equal to nRT over P, right? So how do we calculate V? Well, first we need N. Now we're not given N, but we're given the mass in grams of the gas. And we can convert the mass to moles by dividing by the molar mass. So what I'm going to do here is write down 16.0 grams, and then I'm going to multiply by a conversion factor, which allows us to convert from grams to mole, which means I'm going to need to determine the molar mass of C2H6. So let me do that calculation right now. So in the case of C2H6, the molar mass of C2H6 is 30.07. So down here, I'm going to put 30.07 grams. So basically, by doing that part of the calculation, you're going to end up with the moles. Then we're going to multiply by R, which is 0.0821 liters atmospheres over mole Kelvin times the temperature, which is 18 degrees. Now, 18 degrees Celsius, we have to convert that to Kelvin. So we have to add 273 to that. And when I did that calculation, I end up with 291 Kelvin. So that goes here. And then I'm going to divide all of that by the pressure. Now the pressure is given in torrs. What we have to do is convert that to atmospheres. And if you remember from earlier in this chapter, we saw that 1 atmosphere is equal to 760 torr. All right. So that's basically the setup. And we can see certain units canceling. The gram units will cancel out here and here. The mole will cancel out here and here. The Kelvin will cancel out here and here. The atmospheres will cancel out here and here. And the torr will cancel out here and here. So your final unit would be liters, all right? So let me do the calculation here. 16 divided by 30.07 times 0.0821 times 291 divided by 720 divided by 760. Okay, so according to my calculations, this works out to be equal to 13.4 liters. So 13.4 liters. And that's it. That's basically how that is done. All right, so this one is a bit more challenging because we have to do some conversions from grams to moles and then from, excuse me, Celsius to Kelvin and torr to atmospheres. But pretty much the setup is similar to what we saw in the previous example. Okay, any questions about this example? Any questions? Any questions?
No questions.
All right. Okay, so some applications of the ideal gas equation. We can actually use this to calculate not only, certain, hold on 1 minute. We can use this not only to calculate, certain variables like volume and temperature and so on, but we can also use it to determine the molecular mass of a gas. And later on, we're going to see that we can also use it to determine the density of a gas. But let's focus on molecular mass, all right? So first thing I'm going to say here is that I'm going to let uppercase M be equal to the molar mass and lowercase m be equal to the mass in grams. So if we're going to use these terms to represent these different items here, then we can say that the number of moles of a gas can be equal to the mass in grams divided by the molar mass. In other words, lowercase m divided by uppercase m, all right? We can also have an expression for N based on the ideal gas equation, right? N is equal to PV over RT. That's basically the ideal gas equation. So here we have two things that N are equal to. N is equal to the mass in grams divided by the molar mass, and it's also equals to PV divided by RT. So we can set this being equal to this, and that's what we have right here. And then we can rearrange it to solve for uppercase M, which is a molar mass. And when we do that, this is the expression we end up with. Uppercase M, the molar mass, is equal to the mass in grams times R times T divided by P times V, right? And so that's basically an equation you can use to determine the molar mass of a gas. So if you know all these terms on this side of the equation, all you have to do is plug the numbers in and you're going to get your value for M, all right? Okay, so here is an example utilizing what we just learned. And these writings were done before because I was recording a video using this example. So the question says, if 0.550 grams of a gas occupies 0.200 liters at 0.968 atmospheres and 289 Kelvin, what is the molecular mass of the gas? Now, let me just say one thing, just to remind you of something that we talked about, if I remember correctly, in chapter 3. Remember that the molecular mass of any substance is the same as the molar mass. The only difference between them is the units, but numerically speaking, they're the same. Is there a question? Hello, is there a question? Okay, tell you, if there's any noise in the background, please mute yourself, or better yet, maybe I should mute, I don't know who it is. Oh, okay, you're both muted, okay. All right, so, as I was saying, so this question is, gives you the mass in grams, it gives you the volume in liters, gives you the pressure in atmospheres, and gives you the temperature in Kelvin. And the question is asking for the molecular mass. And I was making a point that the molar mass and the molecular mass are numerically the same. The difference between them would be the units. Now, the equation that we have here is for the calculation of the molar mass. So all we have to do is plug these numbers into this equation in their correct places, and that will give us the molar mass. So when you plug in the 0.550 grams here, the R here, the temperature here, which is 289, divided by the pressure, which is 0.968, times 0.200 liters, then the calculated answer here for the molar mass is 67.4 grams per mole, right? And therefore, the molecular mass, which is what the question is asking for, is the same answer numerically, but the units would be AMU, all right? So this would be the final answer. The molecular mass is equal to 67.4 AMU. All right, so that's basically how that's done. All right, any questions about this example?
No questions.
All right, so the next example using the same equation. Okay, why is this thing not budging? Okay, good. It's basically the same thing. The only difference is, well, the numbers. And not only that, but the pressure here is given in torr, and the temperature is given in Celsius. So we have to do some conversion here. And the volume is given in mils, right? So we're using the same equation. M, uppercase M is equal to MRT divided by PV. M is 0.523. R, of course, is always going to be 0.0821. And the temperature now is 100 degrees Celsius, which is equal to 373 Kelvin. The pressure is 755 torr, but we have to multiply it by this conversion factor to convert it to atmospheres. And then the 185 mils, we have to multiply it by this conversion factor here to convert it to liters. And then we just put the numbers in the calculator, and the answer here is 87.7 grams per mole. That's the molar mass, so therefore the molecular mass is 87.7 AMU, all right? So very similar to the previous example, but of course, we had to do some unit conversions before we can plug the numbers into the equation and solve for what the question is asking for, all right? So that's one application of the ideal gas law. Another application is we can use the ideal gas law to get an expression for the density of a gas, all right? So first thing I want to mention here is that because gases are much less dense than solid and liquids, the densities typically are expressed in grams per liter, right? So what we're going to start off with is the equation that we were working with for the previous two examples, which is this equation right here. And we can rearrange it to get M over V on one side, which is the density, and that would be equal to MP divided by RT, right? So M over V, as I said before, is the density. So therefore, this would be the final expression for the calculation of the density of a gas. The density is equal to M, which is the molar mass, times P, which is the pressure, divided by R, times T, which of course is the temperature in Kelvin. And there are a couple of things that you'll notice about this equation in terms of the relationship between densities and the other variables on the other side of the equation. For one, the density is directly proportional to the molar mass, right? So what that means is that everything else being equal, the greater the molar mass of a gas, the greater will be its density. We also see that the density is directly proportional to the pressure, right? So the greater the pressure, the greater the density of the gas. And we can see that the density is inversely proportional to the temperature, right? In other words, the higher the temperature of the gas, the lower will be the density of the gas, all right? So those are just some relationships that one can observe based on this equation right here. Okay, so here's an example using that equation. This is the equation right here. The question gives us the formula for the gas, the temperature of the gas, and the pressure. So we can calculate the molar mass based on the formula. So if you add up the molar masses of carbon and hydrogen according to this formula, you're going to get 16.04 grams per mole, multiplied by the pressure, which is 0.978 atmospheres, divided by the R value, which is always 0.0821, times the temperature, which is 25 degrees Celsius. So that converted to Kelvin will give us 298 Kelvin. And then when you do your number crunching, you're going to end up with your answer being equal to 0.641 grams per liter. And that's basically how that is done. All right. Any questions about this example? Any questions?
No questions.
Okay, so the next example, same equation being used, but this time the question is asking for the pressure. They gave you the formula for the gas, which is O2. They gave you the temperature, and they gave you the density, right? So this is the equation that we're using. This is what the question is asking for, which is the pressure. So we're rearranging this equation to get P is equal to DRT over M, right? That's the equation that you get when you solve for P on one side. And then we put the numbers in. So the density is 1.50 grams per liter times R times T, which is, again, 298, 25 converted to Kelvin, divided by M, uppercase M, which is the molar mass, which is 32.00 grams per mole, right? Because it's O2. And then after the number crunching, you're going to get your answer being equal to 1.15 atmospheres. All right? So that's basically how that is done. So as you can see, for all these equations here, it's all a matter of identifying the terms in the questions and plugging the numbers in to get your final answer. And you'll be getting, of course, in assignment number 5. Let me just check something here. Let me go back to Canvas.
Mr. Nasser, did we do assignment number 4?
Hold on 1 minute.
Because I was looking for that one and that one wasn't posted.
Let me see here. Okay, so apparently I never, let me publish assignment number 4 right now. Right. Okay. As far as assignment number 5 is concerned, okay, I'm just checking to see the type of, okay, so most of these questions, at least in the first part, the first 7 questions, is basically similar to what we were doing so far. So up to this point, you can, in fact, let me publish this right now. You can attempt all questions up to question number 7. Let me publish this here. All right, so I'll set the due date for these shortly. All right. Okay. All right. So let me go back to our lecture here, PowerPoint, and let's talk about another particular law. And this law is called the law of combining volumes. And this is very important because we're going to look at combining 2 concepts. The first concept are basically all the laws governing the behavior of gases, and we'll be combining that with what we learned in chapter, I think, 3, when it comes to stoichiometry, all right? So let's talk about this law, the law of combining volumes. So the law is what you have right here. It says when gases measured at the same temperature and pressure are allowed to react, the volumes of the gaseous reactants and products are in small whole number ratios. And the whole number ratios is very important because we can actually determine what those whole number ratios are based on the stoichiometry of the equation. So for example, if you have a reaction between hydrogen and oxygen to form H2O, right? So let me write that equation down here. Let me see if I can squeeze it right here. So it's H2 gas plus O2 gas to give H2O gas. And let's balance this equation here. So to balance this, we need a 2 here and we need a 2 here, right? So as stated here, at any given temperature or at a given temperature and pressure, the volume of hydrogen is 2.00 liters and it will react with 1.00 liters of oxygen, right? Hold on, sorry about that. So in other words, there's a 2-to-1 ratio between the hydrogen and oxygen as far as the volumes are concerned. And that mirrors the 2-to-1 ratio that is shown in the balanced equation as far as the coefficients are concerned, right? So basically the small whole number ratio that is observed when it comes to gases reacting at the same temperature and pressure is basically the whole number ratio represented by the coefficients of those same substances in the balanced equation, right? So that's basically what this law is basically stating. For the balanced equation, the coefficient represents the volume ratios of the different gases involved in the reaction. Here's another example, the reaction between nitrogen and hydrogen to form ammonia, all right? So in this case, I'm not sure where I can squeeze this. In fact, let me get out of this here and bring this up. So in the case of the reaction between nitrogen and hydrogen, it's N2 plus H2 to give NH3, all right? And these are all gases, all right? So to balance this, we're gonna need a 2 here and a 3 here, all right? So basically, going back to the PowerPoint here, they stated here that as far as that reaction is concerned, the volume ratios, well, let's look at the actual volumes that is used here. It says 6 liters of hydrogen will react with 2 liters of nitrogen to form 4.00 liters of ammonia. So that's a 6:2:4 ratio. So if we go back to this here, you'll see that the ratio, based on the balanced equation here, it's a 1:3:2 ratio. Now the question says, or the statement that is given says that the volume of the hydrogen is 6.00 liters, for the nitrogen is 4.00 liters, and for the ammonia, it is, no, this is 2.00 liters, I'm sorry. And this is 4.00 liters, all right? So that basically the volume ratios here, 2 to 6 to 4, is basically the same thing as 1 to 3 to 2. So again, we see that the volume ratios parallels the mole ratios as given in the balance equation, right? And that's very useful in terms of calculating volumes of gases involved in reactions. In fact, I think the next example deals with that. But before we get to that example, let me just make one final statement here as far as this law is concerned, and that is that we don't need to know the actual conditions for the reaction as long as it's the same conditions applying to all the gases, right? So in other words, we don't need to know what the temperature and pressure of the gases are as long as the temperature and pressure of all the gases are the same, right? As long as that is the condition that is held fixed, then the volume ratios would be the same as the mole ratios. And just to illustrate this further, this is a pictorial representation of the first reaction I talked about, the reaction between hydrogen and oxygen to form water, right? So these are your hydrogen molecules here in these vessels here. And by the way, all these vessels have the same volume. So basically what this is saying is that 2 volume units of hydrogen will react with 1 volume unit of oxygen to form 2 volume units of water. So basically it parallels the mole ratios given in the balanced equation, right? So as stated here, the volume ratios will be the same as the mole ratios, as long as the temperature and pressure are all the same, all right? So that's basically what Gay-Lussac's law is all about. So we can use that to do this example where it says how many liters of oxygen are consumed for every 10.0 liters of carbon dioxide produced in the combustion of liquid pentane if all the gases or all the volumes are measured at STP. So STP, of course, stands for standard temperature and pressure. But what the point being made here is that the temperature and pressure are constant for all the gases involved. So the first step in this process would be what? What would be the first step you would take in order to answer this question? Anybody? What would be the first step? Well,
I'm stuck.
You're given this question. It talks about the fact that you have a combustion of pentane. It's asking for the volume of oxygen. So what would be the very first thing you would do in order to answer this question?
Would we write out the equation?
Exactly. The balanced equation. So my next question for you guys is, what would be the reactants based on the information provided? What would be the reactants in this equation? Well,
would it be C5, C12?
C5H12. Okay. And what will it react with? Let me change my color here.
The oxygen.
Okay, so it will react with O2. And what would be the products?
CO2.
Okay, one of them would be CO2. And what would be the other product?
H2O, water.
Exactly. So H2O. And then the next step is to balance it. So how would you balance this equation?
You would put 5 in front of the CO2 or
Okay.
in front of the C.
Yeah. Mm-hmm.
And then you would put
how would you balance the hydrogens?
would it be would it be 6 in front of the H2O?
Okay, very good. And then what?
Then the oxygens.
Mm-hmm.
That's would you put a 3 in front of the O2?
Well, let's think about it. How many oxygens do we have total on the right side?
2, 3.
Hmm?
Wait,
How,
you have to multiply the 2 by 5, right? To get
okay,
10
right. 10, right? Plus?
plus that one oxygen, which is 11, right? At the
Nope.
end.
You have a 6 here.
Oh,
So what's the total number of oxygens on the right side?
16.
16. So how would you make this 16 on the left side?
You would put 8.
Exactly. And that's it. So that would be the balanced equation, right? So we needed to do that before we can do anything else. So let me erase these marks here. So the next step now is we have to write down what is given, which is 10.0 liters of CO2. And the question is asking how many liters of oxygen will be produced or consumed, I should say. So we start off with the 10.0 liters of CO2, and we have to multiply by the appropriate volume ratio, which represents the volume ratio between the carbon dioxide and the oxygen. And as you can see, for every 5 moles of carbon dioxide produced, 8 moles of oxygen would be consumed. We can use liters instead of moles, and therefore we can put 5 liters of CO2 down here, 8 liters of oxygen above, and then we do the number crunching, and that will give us 16.0 liters of oxygen. And that's basically how that is done. All right. So that's how this example is tackled. Any questions about it? Any questions?
No
Any
question.
question? All right. So let me see here. Okay, so the next thing we need to talk about is using the ideal gas equation in gas stoichiometry, because what you'll find is that when it comes to gas stoichiometric problems, it is not as easy as the one that we just looked at. The reason why the one that we looked at just now could be done so easily is because the temperature and pressure of all the gases in that particular situation are the same. But if that's not the case, then we would have to take a different route in order to solve problems like that. So, okay, all right. So as stated here, we can only use the law of combining volumes if the temperature and the pressure of all the gases are the same. Otherwise, we have to resort to the same approach that we took in chapter 3, combined with the ideal gas equation. And that's what we're going to look at in the example that's coming up. So if you recall, in chapter 3, basically stoichiometric problems comes down to this approach. You have the moles of one substance, you need to convert it to the moles of the other substance, and we have to multiply it by its appropriate mole ratio, right? And of course, you may have to do some calculations before we get to the moles of substance A, and some calculations after we get to the moles of substance B, right? Now, when it comes to gas stoichiometric problems, then we would have to use the ideal gas equation if we are given the pressure, volume, and temperature of the gas. So for gas A, for example, if we have P, V, and T, then we can use the ideal gas equation to find N, which is the moles of substance A. And then we multiply by the mole ratio to get the moles of substance B. And then depending on what the question is asking, the question could be asking for you to find the pressure or the volume or the temperature of substance B, which means that you have to use the ideal gas equation applied to substance B, all right? So that's basically what is involved in a typical stoichiometric, gas stoichiometric type problem. So here is an example. So this question is talking about the decomposition of a compound, which I don't think they use this anymore, but back in the day, they used to use this reaction to deploy those air safety bags, airbags in cars. Basically what the mechanism, the way it works is that when the crash happens, basically the sodium azide would be subjected to a shock, and it spontaneously reacts to form nitrogen, which fills out the airbag, all right? But I don't think they're using this method anymore. I think they're using something else. But in any case, this is the balanced equation for the reaction, right? And the question is asking, what volume of nitrogen measured at 25 degrees Celsius and 0.980 atmospheres is produced by the decomposition of 62.5 grams of sodium azide? So basically, you're given 62.5 grams of sodium azide. I'm sorry. Let me erase this here. This should be N3. And it's asking for the volume, presumably in liters, at 25 degrees Celsius and 0.980 atmospheres. Okay, so what I would do is I would start off with 62.5 grams of sodium azide. And what I would do is convert that to moles, which means I need to multiply this by 1 mole of NaN3 divided by the molar mass. So let me do a calculation here of the molar mass of NaN3. Hold on 1 minute. NaN3. Okay, so according to my calculations, the molar mass of NaN3 is 65.01 grams. So that's a setup for that. And then I'm going to write down another conversion factor, which represents the mole ratio between the nitrogen and the sodium azide. As you can see, that's a 3:2 mole ratio. So the way we would represent that here is that we're going to have 3 moles of nitrogen above and 2 moles of sodium azide below. And we work that out to get the moles of nitrogen. So 62.5 divided by 65.01 times 3 divided by 2. So according to my calculations, this works out to be equal to 1.44 moles of nitrogen. All right. And then now, to get the volume, that's where the ideal gas equation comes in. V would be equal to nRT over P. So N is equal to 1.44 moles times R, which is 0.0821 liters, atmospheres, over mole Kelvin, times the temperature. And according to the question, the temperature is 25 degrees Celsius, which we have to convert to Kelvin, which is 298 Kelvin. And we divide all of that by the pressure, which is 0.980. And that's it. The mole units will cancel out here and here. Kelvin will go here and here. Atmospheres will go here and here. So your final answer would be in liters, which would be the unit of volume. So 1.44 times 0.0821 times 298 divided by 0.980. So according to my calculations, this works out to be equal to 35.9. So 35.9 liters, all right? And that's how that is done. Okay, any questions about this example? Any questions? Any questions?
No questions.
Okay, so now all the examples that we have looked at so far, we were assuming that we were working with at least one gas at a time if there's more than one gas. But what we'll be talking about here in this section is how do we deal with a mixture of gases? And this is where Dalton's law of partial pressures comes in. And it's an actually simple law. It basically says that if you have a mixture of gases, then the total pressure exerted by that mixture will be equal to the sum of the partial pressures of the gases that make up that mixture, all right? So basically, if you have gases 1, 2, 3, etc., then the total pressure of that gaseous mixture will be equal to the pressure of gas 1 plus the pressure of gas 2 plus the pressure of gas 3, and so on and so forth, right? Now, the term partial pressure basically is the pressure that a gas would exert if it were alone in the container, right? And we can actually calculate that partial pressure using the ideal gas equation to calculate the partial pressure of each individual gas. So this would be the expression for gas 1, this would be the expression for gas 2, and so on and so forth. Hold on 1 minute. Okay, why do people keep calling when I'm otherwise occupied? Okay. Give me a minute. I just need to respond to this person here. I'm sorry. I'm sorry about that, folks. This was kind of an important call, which I can't answer right now. Anyway, okay, so this is how we deal with a gaseous mixture, all right? And this is how we calculate the partial pressures of each gas. And we can add these together to get the total pressure. Now, I want to show you what will happen when we add these terms together. So I'm going to get out of this here and go back to this here. And let me just get rid of that. So, as I was saying, this is Dalton's law, P1 plus P2 plus P3 plus all other gases to the nth gas, Pn, right? So if I were to substitute, now remember, P is equal to nRT over V, right? So if I were to substitute for each of these terms here, this expression, then this is what I'm going to end up with. N1 RT over V plus N2 RT over V plus N3 RT over V plus all the way to NN RT over V, all right? So that would be the result of adding all these terms. You're going to end up with this expression right here. And then what you can do from here is factor out RT over V, and this is what you're going to end up with. You're going to end up with N1 plus N2 plus N3 plus N, I'm sorry, let me erase this here, plus all the way to NN multiplied by RT over V, right? So this here is basically the sum of the moles of all the gases in the mixture, so we can replace that with NT. So the final equation for the total pressure of the gaseous mixture will be equal to the total number of moles times R times T divided by V. So this is another expression that you need to be aware of, which is the consequence of the ideal gas equation applied to each gas and Dalton's law, all right? So what this is telling you is that the total pressure of a gaseous mixture would be equal to the total sum of the moles of all the gases in the mixture times R times T divided by the volume, and that will give you the total gaseous pressure of the gaseous mixture, all right? So that's another expression that you need to be aware of. Okay, so let me go back to the PowerPoint here, and let me see here. Okay, so let's apply what we have just learned to this example. So this question says a 1.00 liter sample of dry air at 25 degrees Celsius and contains 0.0319 moles of nitrogen, 0.00856 moles of oxygen, 0.000381 moles of argon, and 0.00002 moles of carbon dioxide. So the question is asking for you to calculate the partial pressure of all the gases in the mixture and the total pressure. Okay, so basically, what you'd have to do is basically apply the ideal gas equation to each of these gases. So basically, it's going to be P is equal to nRT over V, right? The color keeps changing. So you'll be applying this equation here to each of the gases, right? So let's do that for nitrogen. The partial pressure of nitrogen will be equal to the number of moles of nitrogen, which is 0.0319 moles times R, which is 0.0821 liters atmospheres over mole Kelvin, times the temperature, which is 25 degrees, which is the same thing as 298 Kelvin, all divided by the volume, which is 1.00 liters. So when I work that out, I'm going to end up with 0.0319 times 0.0821 times 298 divided by 1. So the answer I got here is 0.780 atmospheres. All right. And basically, it's the same calculation. So this will become a bit boring. Same calculation for the other gases. So the other gas is oxygen. The partial pressure of oxygen would be equal to the number of moles, which is 0.0085, whoops, 856 moles times R, which is 0.0821 liters atmospheres over mole Kelvin times the temperature, which is 298 Kelvin, all divided by 1.00 liters. And let's see what that gives. 0.00856 times 0.0821 times 298 divided by 1. Okay, so according to my calculation, this works out to be equal to 0.209, 0.209 atmospheres. And then we do a similar calculation for argon. So partial pressure of argon would be equal to 0.000381 moles times 0.0821 liters atmospheres over mole Kelvin times 298 Kelvin, all divided by 1.00. And work that out. And let's see what that gives. So 0.000381 times 0.0821 times 298. And according to my calculation, this works out to be equal to 9.32 times 10 to the minus 3 atmospheres. And then the last gas, partial pressure of carbon dioxide. So that would be equal to 0.0002 moles times 0.0821 liters atmospheres over mole Kelvin times 298 Kelvin, all divided by 1.00 atmospheres. And let's see what that gives. That gives 0.00002 times 0.0821 times 298 divided by 1. So that gives 4.89, write this out here, 4.89. Actually round off to 1 sig fig, so that should be 5 times 10 to the minus 4 atmospheres. And to get the total pressure, we simply add this to this to this to that. And let's see what that gives. So 0.780 plus 0.209 plus 9.32 times 10 to the minus 3 plus 5 times 10 to the minus 4. So according to my calculations, this works out to be equal to okay, how many sig figs? Actually, how many decimal places? And according to this should be 2 decimal places. So according to my calculations, this works. So when you add all these together, you're going to get 1.00 atmospheres. All right. And that's basically how that is done. Okay. Any questions about this example?
No questions.
All right. We're going to take a break here. So in the next 10 minutes, we'll get back and continue our discussion of chapter 5. All right. So the next 10 minutes, I'll see you guys.
Okay.
Okay, I'm back. So we're going to continue our discussion of partial pressures and Dalton's law. And what I'm about to show you here on the screen is a pictorial representation of how Dalton's law works. So what is being represented here, we have a vessel here, which contains hydrogen gas. This is the number of moles, this is the pressure, and this is the volume and the temperature, right? And then we have another container, same volume and temperature, containing a different gas, helium. This is the moles and this is the pressure. And then the third container represents what happens when you mix these two gases together under the same conditions of temperature and volume, right? And what you'll notice is that basically the pressures are additive as predicted by Dalton's law. So the 2.9 atmospheres plus the 7.2 atmospheres for the helium gives you the total pressure of 10.1 atmospheres, right? And of course, the moles are additive as well, 0.60 moles of hydrogen plus 1.50 moles of helium to give you a total of 2.10 moles of the mixture of gases, all right? So that's basically how Dalton's law works. So there's a question being asked here for you to consider. Let me remove this here. The question is, what would be the total pressure if 0.90 moles of nitrogen were added to this mixture here in C, all right? So to answer that question, all we have to do is find the total number of moles. Okay, where's my, oh, here it is. Okay, so where shall I squeeze this? Let me squeeze this down here. So in this case here, NT would be equal to the total number of moles. Now, before you add the 0.9 moles of nitrogen, the number of moles of gas total will be 2.10. So I'm going to put 2.10 here, moles, plus the 0.90 moles, and that will give 3.00 moles, all right? And then all we have to do to find the pressure, I'm going to squeeze that up here. P would be equal to nRT, and T over RT times RT over V. That's the total pressure. Let me change the color here again. And that would be equal to 3.00 moles times 0.0821 liters atmospheres over mole Kelvin times the temperature, which is 20 degrees, which is the same thing as 293 Kelvin, all divided by the volume, which is 5.0 liters. And whatever that gives, that would be the answer. So let me work that out here. 3 times 0.0821 times 293 divided by 5. So according to my answer, the final total pressure will be 14.4. So the answer here would be 14 actually 14, 2 sig figs. So 14 atmospheres would be the answer, all right? So that's basically how that is done, all right? So basically, as stated here, the partial pressure is related to the number of moles of gas. Basically, it's a proportional relationship. The greater the number of moles of all the gases in the mixture, the greater will be the partial pressure, all right? Okay, so let's talk about another way of expressing concentration. We learned about molarity, but there's another way of expressing the concentration of a mixture, and this applies to pretty much any kind of mixture, but we'll be applying it to gases. It's called the mole fraction. So what do we mean by the mole fraction? Well, the mole fraction is the fraction of all molecules in a mixture that are of a given type. And we can calculate it using this formula here. The mole fraction of gas 1, if gas 1 is one of many gases in a mixture, is equal to the number of moles of that gas divided by the total number of moles of all the gases in the mixture, all right? And you'll notice that the units here for N1 will be moles, the unit here for N total will be moles, So therefore, the mole fraction will have no units, right? So that's one thing you need to know. The other thing you need to recognize is that because this is a fraction, that means that the possible range of values for mole fraction of any substance in a mixture would go from 0 to 1, all right? So basically, you cannot have a mole fraction that is greater than 1, obviously. Now, since pressure is directly proportional to the number of moles, when it applies to gases, then we can represent the mole fraction as being equal to the pressure of gas 1 divided by the total pressure of the gaseous mixture, all right? So there are two ways of calculating the mole fraction. You can calculate it based directly from the definition, or in the case of gaseous mixtures, you can calculate it based on the pressure of a particular gas divided by the total pressure of the gaseous mixture. And we can actually rearrange this equation to find the pressure of a particular gas if you know the mole fraction and you know the total pressure of the gaseous mixture, all right? So that's basically what mole fraction is all about. So based on what we have just covered here, let's look at this example. It says the main components of dry air by volume are nitrogen, and it gives you the percentage, oxygen, and it gives you the percentage, argon, and it gives you the percentage, and carbon dioxide. So the question is asking, what is the partial pressure of each gas in a sample of air where the pressure of that sample of air is 1.00 atmospheres, all right? So the equation you'll be using is P1 is equal to X1 times P total, right? Now, in this particular case, each of these percentages would represent the mole fraction for each gas, right? So if I were to calculate the pressure, the partial pressure of gas 2, I'm sorry, of N2, that would be equal to the mole fraction of N2 times the total pressure, which would be equal to this percentage, which we can express as 0.7808 times the total pressure, which is 1.000 atmospheres, and that will be equal to 0.7808 atmospheres. And we basically do the same thing for the other gases. So in the case of oxygen, the partial pressure of oxygen will be equal to 0.2095 times 1.000 atmospheres, and that will be equal to 0.2095 atmospheres. And then in the case of argon, that would be equal to, okay, so 0.0093 times 1.000 atmospheres, and that will be equal to 0.0093 atmospheres. And then finally, in the case of carbon dioxide, the partial pressure of carbon dioxide will be equal to 0.0004 times 1.00 atmospheres, and that will be equal to 0.0004 atmospheres. And that's it. So these are the answers for the respective gases in the mixture, all right? Okay, any questions about this particular example? Any questions?
No questions.
Okay, so let's move along. So we can apply Dalton's law when it comes to collecting gases over water, which is actually a practice that is oftentimes used as a method of collecting a gas. Now, let me just say that this method only works for gases that are not very soluble in water, right? So this would work for gases like oxygen, nitrogen, hydrocarbon gases like methane and so on, right? This method would work. It will not work for collection of gases like ammonia or hydrogen chloride or chlorine, because those gases will actually dissolve in water and react with water, right? So the method that I'm describing here only works for gases that are very insoluble in water, right? Like oxygen. So the way this works is that you have a jar, which is completely filled with water, which is inverted into a trough, which is also has water in it. You have a tube leading from the reaction vessel where the reaction is taking place, and that tube is led into the jar like this. When the reaction is taking place, it generates a gas, and the gas will be led into the jar and will accumulate above the water surface. So basically the water will be pushed down, and the gas will be collected over here, right, on top of the water. It will not dissolve in the water, and you can collect enough gas until the liquid level or the water level inside the jar is the same as outside. Now, the reason why you do that is because you want to ensure that the pressure of the gas that is collected here, it will be equal to the barometric pressure or the atmospheric pressure acting on the surface of the water outside the jar, right? Now, a very important question is being asked here. It says, what two gases are present above the water surface inside the jar? Now, we know that one of them is oxygen. Now, can you tell me or even guess what the other gas would be? Anybody? One of the gases collected will be oxygen, right? But there's another gas that will be present. And can anybody tell me what that gas is?
Wouldn't it be like carbon, right? Or like hydrogen?
Nope, not carbon, not hydrogen. Any other ideas? Any other guesses you can make?
CO2?
Nope. Let me give you a hint. The gases are being collected. Well, oxygen is being collected over water, right?
Yes.
So what would be the other gas in addition to the oxygen that's present?
I have no clue.
Water vapor. You see what I'm saying? Any liquid, let me make a general statement here. If you have any liquid that is contained in a sealed container, right? Then above the liquid, right? If you have space above the liquid, you're going to have the vapor of that liquid present. You see what I'm saying? So if you have oxygen collected over the water, then the other gas that will be present will be water vapor, right? So as stated here, the gas that is collected, in this case is oxygen, will be saturated with water vapor, right? So if you can determine the vapor pressure of the water that is collected over the water along with the oxygen, then that means that the total pressure of that mixture would be equal to the pressure of the gas collected, which in this case is oxygen, plus the vapor pressure of water, right? And remember I said that if the liquid level inside and outside are the same, that means that the barometric pressure would be the same as the total pressure of the gaseous mixture. So we can equate this to the barometric pressure, which means that the pressure of the gas or the pressure of the oxygen would be equal to the barometric pressure minus the water vapor pressure, all right? So if you know what the barometric pressure is, and if you know what the water vapor pressure is, then the difference between the two would give you the pressure of the oxygen. And that's basically what this equation is saying, right? The barometric pressure minus the vapor pressure of water will be equal to the pressure of the gas that is collected over the water, all right? So that's basically how Dalton's law is applied to this particular situation. Okay, so here's an example, and I think I need to, hold on 1 minute, let me, okay, so here's an example of a problem which applies not only what we just learned in terms of Dalton's law, but also gas stoichiometry. So the question is talking about this reaction here where hydrogen is produced and it says that the hydrogen is collected over water at 22 degrees Celsius when the barometric pressure is 742 torr. And the question is asking what volume of the wet gas will be collected in the reaction of 1.50 grams with excess hydrochloric acid, right? Now, let me just say that there's one piece of information that's missing, and that is the vapor pressure of water at 22 degrees. So let me see if I can find that and include that in this question. So vapor pressure of water at 22 degrees Celsius. Let me see if I can find that. So according to the information I just pulled up here, the vapor pressure, let me write this down here. The vapor pressure of H2O at 22 degrees Celsius is equal to 19.8 torr. All right, that's something that you're going to need in order to answer this question. All right, so unfortunately I did not include it here, but that's what you're going to need. All right, so what I'm going to do is get out of this here and go to my writing application here. Let me get rid of this here. Okay, so according to the question, well, let me write down the balance equation first. So the balance equation is 2Al plus HCl, 6HCl, 6HCl to form 2AlCl3 plus H2, 3H2. Give me 1 minute here. Let me just check something here. Okay, so the question says that you're starting off with 1.5 grams of aluminum, and the question is asking for the volume in liters of H2, all right? Okay, so how are we going to tackle this? Well, what I would do first is start off with the 1.5 grams of aluminum, and I'll convert that to moles. So the molar mass of aluminum is 20, let me not guess. I know it's 26.9 something. I think it's 26.98, but let me not guess. Let me just look it up. So for aluminum, 26.98, I guess correctly. All right, so it's going to be 1 mole of aluminum here and 26.98 grams of aluminum down here. And then the next conversion factor is where we have the mole ratio between the aluminum and the hydrogen. And according to the equation, that's a 3:2 mole ratio. So we're going to have 3 moles of H2 here and 2 moles of aluminum here. All right. So according to my calculations, let's see here, 1.5 divided by 26.98 times 3 divided by 2. So according to my calculations, this works out to be equal to 0.0834. So this would be 0.0834 moles of H2. And that would be the N in the ideal gas equation. Remember, the ideal gas equation is PV is equal to nRT. Now, what the question is asking for is the volume. And the volume would be equal to nRT over P. Now, here's the thing. We know what N is because we just calculated it here. We know what T is because T is given in the question as being equal to 22 degrees Celsius, all right? And we don't know exactly what P is, but we can determine that because according to the question, the pressure of the hydrogen collected over the water, or the barometric pressure, I'm sorry, the barometric pressure, P bar, is equal to 742 torr, right? And we know that the water vapor pressure, which I looked up, is equal to, what was it again? It was equal to 19.8 torr, all right? So this is 19.8 torr, all right? So what that tells us is that the pressure of the hydrogen gas that's collected would be the difference between these two, right? So it's going to be 742 torr minus 19.8 torr. So let me do that calculation. 742 minus 19.8. So according to my calculations, this works out to be equal to 722 torr. And that is the pressure that will go here in this equation. So to calculate the volume of the hydrogen gas that's collected, that will be equal to 0.0834 moles times R, which is 0.0821 liters atmospheres over mole Kelvin, times the temperature, which is 22 degrees. 22 degrees is the same thing as 295 Kelvin. And then divide all of that by the pressure, which is 722 torr, which we have to convert to atmospheres. So 1 atmosphere up here, 760 torr down here, and we work that out, all right? So 0.0834 times 0.0821 times 295, whoops, 295, divided by 720, divided by 760. Okay, so according to my calculations, the final answer is 2.13. 2.13 liters. So this is the answer right here. And of course, some units will cancel out, the torr units will cancel out, the atmospheres will cancel out, the Kelvin will cancel out, and the moles will cancel out. And that's how we arrive at that answer, all right? Okay, any questions about this particular example? Any questions?
No
Any question? Okay, so let me go back to the PowerPoint. And let's see what's next. Okay, so what I'm going to get into right here is just basically some quantitative aspects of the kinetic molecular theory, which we talked about before. Now, if you recall, we said that the kinetic molecular theory is the model that is used to explain all the gas laws and all the observed behaviors of gases, right? And what you're looking at here on the screen are basically the principal assumptions of this particular theory. The first of which is that gases are made up of small particles which are moving very energetically in constant straight line motion, hitting the walls of the container and occasionally hitting each other. The second assumption is that on average, the molecules are far apart from each other. So basically, if you have a gas collected in a container, most of that container or most of the gas, most of it is empty space, basically, all right? The third and very important assumption is that there are no intermolecular forces that exist between the particles excepting when they collide, all right? And then the fourth one is that whenever you have collisions between molecules in a gas, you will have transfer of energy from one to the other, right? However, the total amount of energy will remain constant. And the term used for that, and this is a term that is used in physics, is that the collisions are elastic. In other words, you'll have the direct transfer of energy from one particle to another when they collide, but in total, the amount of energy before and after collision will be the same, all right? So those are basically some assumptions of the kinetic molecular theory. Now, based on those assumptions, we can derive this equation. Now, you don't need to memorize this, and I'm not going to show you how this equation is derived. All I'm going to say is that this equation here is as a result of the assumptions that we were talking about in the previous slide. And let me just explain what each of these terms mean. So P is the pressure, uppercase N here represents the number of molecules, V represents the volume of the gas, M here represents the mass of each molecule, and then we have this special term here, U squared with a bar above. What that means is that we're talking about the average of the squares of the speeds of the molecules. So let me explain further what that means. Basically, what this means is u squared, I'm sorry, let me change this here. Why is this thing not cooperating? Okay, so u squared bar is equal to the square of the speed of gas 1 plus the square of the speed of gas 2 plus the square of the speed of gas 3, and so on until you get to the nth gas molecule. So I'm going to put n here, right? And then we divide all of that by n, all right? So basically what you're going to do is take molecule 1, squared speed, same thing for molecule 2, same thing for molecule 3, and so on until you get to the nth molecule. You add them up and then divide by the total number of molecules, and that gives you what we call the mean of the squares of the different molecules present in a gas, all right? So that's what that means, right? So, sorry about that. All right, so that's basically what this equation is saying, right? And based on this equation, we can derive this equation here. And this equation relates the kinetic energy of the molecule to the temperature expressed in Kelvin. And again, you don't need to know this equation, but I need to show you so that you understand the relationship between the kinetic energy and the temperature in Kelvin. So what this equation is saying is that the average kinetic energy is equal to 3/2 times R, which is a molar gas constant, divided by Na, which is Avogadro's number, which is also a constant, times temperature. So basically, what we have right here is a collection of constants right here. So we can basically just call this one big constant, which is represented here. So what that tells us is that the average translational kinetic energy is directly proportional to the temperature in Kelvin, right? So what that means basically is that the higher the temperature of a gas, the greater would be the average kinetic energy. All right, so that's basically the result of the kinetic molecular theory. As I said before, you don't need to know these equations, but you do need to know the relationships between, for example, the kinetic energy and the temperature. In fact, let me go back to the previous equation here. In this equation here, you will see, for example, that the relationship between the pressure and the speeds, oh gosh, where is this thing? Okay, so this is the pressure right here, and this is the mean of the squares of the gas particles. So what that tells us is that the greater the average squares of the gas particles, the greater will be the pressure, which makes sense if you think about it. The greater the speeds of the molecules, the harder they will hit the container walls, and therefore the greater the pressure that will be exerted by the gas. Another relationship one can see here is that there's a direct relationship between the pressure of the gas and the number of molecules, again, which that makes sense. The number of molecules increase, then the greater will be the pressure exerted, because greater number of molecules will result in greater collisions with or more frequent collisions with the walls of the container, and therefore the pressure would increase. And then here we see that there's an inverse relationship between the pressure of a gas and its volume. Again, that makes sense. That's Boyle's law, right? If you were to reduce the volume, that means that the average distance traveled by the particles would be shorter, and therefore they will collide with the walls of the container more frequently, and therefore exert a greater pressure on the walls of the container. All right, so those are just some relationships that we can explain based on the kinetic molecular theory. Okay, so let me move on now to a discussion of molecular speeds. We alluded to it earlier, because if you think about it, whenever you have a sample of a gas trapped in a container, as you can imagine, not all the molecules in that sample will travel at the same speed, right? Some will be traveling at a slower speed, other will be traveling at faster speeds, right? So we basically have to decide on how do we represent the average of the speeds of the molecules. And that's where this term comes in, the root mean squared speed, which is represented by URMS, right? And that is the square root of the average of the speeds of the molecular, of the molecules. So if you remember, I mentioned, let me squeeze it in over here. All right. So remember I said that U squared average, U squared average, erase this here. Okay, remember I said that the average of the squares of the speeds of the molecules will be equal to U squared for molecule 1 plus U squared for molecule 2 plus U squared for molecule 3 all the way to U squared for molecule N, right? So that's the mean of the squares of the molecules. Then the root mean squared speed, as stated here, would be the square root of that value, right? And it turns out that it is equal to, one can prove it, but I won't show you. That is equal to this part right here, 3RT over M, all right? Where R is the molar gas constant, T is the temperature, and M is the molar mass. Now here you have to be careful, and this is where I mentioned before that there's a different value of R that you'll have to use in this particular case. If you're going to use this equation to calculate URMS, or the root mean squared speed, then you have to be careful about using the correct units associated with R. In this case here, R would be equal to 8.31 joules per mole Kelvin. All right. So we have been familiar with using the other value of R. We have been using this value of R, 0.0821 liters atmospheres over mole Kelvin. This is the value of R that we have been using all along, right? In all the equations that where R appears. However, in this case here, you cannot use this value of R. You have to use this value of R, all right? So that's one thing about this equation that you have to be careful about. Use the value of R, which is equal to 8.31 joules per mole Kelvin. Another thing you have to be careful about is the units of M. In this case here, M, whatever the molar mass is, it must be expressed in kilograms per mole, all right? So you cannot just express M in grams per mole, which is what we're used to. We have to express M in terms of kilograms per mole. So what that means basically is that you have to convert whatever molar mass you calculated, you have to convert from grams to mole to kilograms per mole by dividing by 1,000. Now, what I'm going to do now is show you why we have to make those two special precautions when we're using this equation. So let me get out of this here. And let me go back to my writing tablet here. Let me get rid of this here. Okay, so the equation that I just showed you is this. The root mean squared speed of the gas will be equal to the square root of 3RT over M, all right? Whoops, M. Now, what I'm going to do is show you why is it that R must be expressed in joules per mole Kelvin and M must be expressed in kilograms per mole. Now, the first thing I'm going to mention here is the joule unit. The joule unit, we're going to see this later on in chapter 6, but let me just introduce this to you now. The joule unit is the same thing as kilograms meter squared over second squared, right? So whenever you see joule, it's the same thing as this collection of units, right? So what I'm going to do, instead of putting numbers here into this equation for these terms, I'm going to put the actual units, right? And then you're going to see what the units of the root mean squared speed will work out to be, right? Now, 3 has no units, so we're going to leave that alone. R, as I said before, would be joules per mole Kelvin. Joules is the same thing as kilogram meter squared per second squared. So for R, I'm going to put, for the units of R, I'm going to put kilograms meter squared over second squared joules, mole Kelvin. right? And then I'm going to divide that, I'm going to multiply that by the units of temperature, which would be Kelvin. And then I'm going to divide all of that by the units of molar mass, which, as I said before, must be expressed in kilograms per mole. So let me put kilograms per mole down here. Okay, so I'm going to work this out. Some units will cancel out, namely the kilogram units, the mole units, and the Kelvin units. And what we're left with is the square root of meter squared over second squared, which would be equal to meters per second, which would be the units of speed. All right? So that's basically how we determine the units of speed based on the appropriate units for R, which, as I said before, is joules per mole Kelvin, and for molar mass, which is kilograms per mole. So I just thought it was important that I show you this so you know the reason why the R value must be expressed in joules per mole and the molar mass must be expressed in kilograms per mole. Okay, so with that out of the way, let me go back to this here. Some final comments about this equation. As stated here, typically the molecular speeds are high on the order of 1,000 meters per second. So you might have some average workout to be less than 1,000, maybe about 900 or 800 meters per second. And in some cases, they'll be higher. And then another important thing I need to mention here concerning this equation is the relationship between the root mean squared speed and the molar mass, right? As you can see, it's an inverse square root relationship. So what does that mean? That means basically that the molecules with a heavier molar mass will move at a slower speed on average if the temperature is the same, right? So as stated here, at a fixed temperature, molecules of higher molar mass will move more slowly than molecules of lower molar mass, right? So basically, heavier molecules move more slowly, lighter molecules move more quickly at the same temperature, all right? Which makes sense if you think about it. Okay, now what I want to show you here, let me see how much time I have left before the next break. Let me see here. Okay, I think we should be able to finish this before the next break. Okay, now what I want to show you here are two different graphs, right? And these graphs represent a plot on the y-axis of the relative number of molecules, and then on the x-axis, the speeds of the molecules, right? And as you can see for these different gases, oxygen, methane, and hydrogen, you have different plots, right? And as I said before, for any gas, the molecules will be moving at different speeds. So there's a distribution which is represented by the curves here. So in the case of oxygen, you have this pink line here, right? In the case of methane, you have this, looks like a blue line here, which represents the distribution of the molecular speeds. And then in the case of hydrogen, it's a more flatter distribution right here, all right? Okay, now the good thing, one thing I like about this graph right here is that it shows you the relative speeds of the molecules as it relates to the molar mass, right? Now, how do we determine the molar mass? Or I should say, no, let me take that back. How do we determine the mean squared speed, the root mean squared speed? Well, when it comes to this plot, I'm sorry, I'm mixing up my words. When it comes to this plot, what you do is you take the apex of the plot or the maximum point of the plot, and then you drop a vertical line down. Now, please forgive me, this won't be exactly a straight line because I'm doing this freehand. You drop a vertical line down until it cuts the x-axis. So it cuts x-axis here, right? Now, by my estimation, let's see here, what would be the value here? This is 1,000, this is 500. So I would say this is about 400 meters per second, right? So that would be the average speeds of the oxygen molecule, right? And then in the case of methane, do the same thing. You drop a line from the maximum point there until it cuts the x-axis. So I would estimate that this is about what? I would say this is about okay. Can you hear me, Mr. Perez? Can you hear me? Hello? Hello, hello, hello? Hello? Hello, Mr. Perez? Can you hear me? Okay, what I'm going to do is basically finish up on this section and record it and publish it in Canvas so that you guys can have it to look at, all right? Okay, so as I was saying, to get the root mean squared speed for the separate gases in this particular graph, in the case of methane, we did a case for oxygen, that's about 400 meters per second. In the case of methane, that's about, let me see here, that's about 700, give or take, meters per second. And in the case of hydrogen, we do the same thing. Now, in this case, this seems to be about 1,500 meters per second, all right? And you'll notice that as you go from oxygen to methane to hydrogen, the speeds increases, and that's because the molar mass decreases. Oxygen has a molar mass of about 32, methane has a molar mass of about 16, and hydrogen has a molar mass of about 2. So basically you see there the inverse square root relationship between the molar masses and the root mean squared speed. Now the graph here to the right talks about the relationship between the temperature and the root mean squared speed for one gas, in this case, oxygen. So let's do the same thing. So in the case of the temperature 273, the root mean squared speed is 400 meters per second. At 1000 degrees, the root mean squared speed is about, I would say about 600 meters per second. And then here at about 2000 Kelvin, the maximum is about here. So that looks like about, I would say 1400 meters per second. So in this case, as you can see, as the temperature increases from 273 to 1000 and then to 2000, there's a corresponding increase in the root mean squared speed as you go from 400 to 600 to 1400. All right. So that shows you the relationship between the molecular speeds and the temperature in the case of the graph to the right. In the case of the graph to the left, it shows you the relationship between the molar mass and the root mean squared speed. Okay, so the next topic we're going to talk about here is diffusion. I'm going to stop here and see if I can reconnect with you guys. So I'll just take a break of about 10 minutes to do so. All right. Okay, Mr. Perez, can you hear me? Going once, going twice. All right. What I'm going to do is post the videos covering the rest of the topics for this chapter. And I'm going to make an announcement in Canvas concerning what we're going to do from now on, because this is the second time this has happened. All right. Okay, bye.